So you can use that. Okay. Are there any questions? It's been a while since I've seen you.
It was for 3-1 and 3-2?
3-1, we are going to do 3-2. We're going to talk about 3-2.
That was, okay.
So I think I said read some of the section. It's a good idea to get a little bit of a jump on reading some of that stuff, even if you're confused. Read some of it, be confused, we'll talk about it again, and then read it again, maybe a little less confused.
The only one on, yeah.
Oh, that's it, yeah, it gets a little hairy, there's some detail. We're going to go over some of it today.
Okay. As far as the 3-1 homework goes, the only one I want is just like, it's just about knowing my trig identity. This number 24. I'm checking for linear independence.
Oh, okay, so 3.1, number 24?
It's just kind of like, because I'm lefty on.
Right, and you know, this class doesn't require, I have to keep that in mind, you know, this class does not require linear algebra as a prerequisite. So some of the stuff that we talk about, linear independence, if you've taken linear algebra, great, you understand on a different level. We're going to talk about it and say, okay, linear independence means, well, if there's just two functions, then neither of them is a constant multiple of the other.
What I'm getting at is that this problem is dependent according to the book, but I think because I couldn't draw in my switch it to my switch that I was using now.
So what are the functions they gave?
First one is sine squared x.
Okay.
Second one is 1 minus cosine of 2x.
1 minus cosine 2x. Okay. Yeah, and you can just writing it down, you feel that there are, of course, identities that may come into play. So it's the Wronskian of y1 and y2. We form this sort of matrix. We're just interested in the determinant of it, but y1, y2, I lay those across. We got sine squared and 1 minus cosine 2x. And then their first derivatives. So what's the derivative of sine squared?
Cosine x, cosine x.
2 sine x cosine x, and that can be written as an identity of the double angle for sine. This one, that's going to drop out. Minus, and the derivative of cosine is negative sine. So I'm going to have sine 2x, and then the chain rule would pop out a 2 there. It would be positive, right? Cosine and negative sine, but I got the minus and negative sign. Okay. Double negative, yeah, it'll make that positive. All right, and then the Wronskian is product at minus the other diagonal product. So we're going to have 2 sine squared x times sine 2x. Okay, and yeah, there's obviously going to be some trig identities we can sort of maneuver. And then this one is going to be sine, if I distribute sine to that, sine 2x minus sine 2x cosine 2x?
Yes.
No?
No, never mind.
This is where I said
I don't know, maybe not. And we bailed out there. Sine 2x, maybe I should have written that as, you know, maybe we should use the double angle formula. And that alone would be 2 sine x cosine x. I got a 2 right there, so I'm going to have 4 sine squared x and 2 sine x cosine x. So another sine x cosine x. I could collect the sine x, call that sine cubed x. Get rid of that one and write this as times cosine x. Minus, and I don't know if that's going to help you anywhere. Minus sine 2x. Oh, geez. Cosine double angle somewhere. I don't know.
You're wrong, but you didn't on the trig identity.
Yeah, it does.
Well, if you leave it as sine 2x, you can factor that out.
Yeah, well, yeah, I did not know, and I multiplied that out, so maybe I don't. Yeah, I got to, someone told me maybe not multiply that out. Sine 2x, 1 minus cosine 2x. And there's a double angle for cosine that I don't remember. I never remember the double angle for cosine. It's something weird. Anybody know? Is there in a book?
Cosine squared minus sine squared.
In the calculus book.
Is it cosine squared minus sine squared, or 1 minus?
Is this the one
One
with the
minus
three
sine
and
squared.
cosine squared?
But I don't think that's double angle, is it?
No, the double angle definitely has a minus
I
n.
mean, sine squared plus cosine squared
Equals
equals
2
1.
sine squared.
Derive a bunch of them from that.
There's a one that's a minus in between them. That might be the double angle.
Oh, it's two cosine squared x minus 1, or 1 minus 2 sine squared x.
1 minus 2 sine squared. That sounds promising. Okay, that's that.
Oh, yeah, because that'll do it.
Because I want the sine cubed.
Oh, but if you don't, if you just continue, just factor out the sine squared, the sine of 2x, and then you have a sine of x squared minus the sine of x squared.
Where at? So I'm subtracting out.
Oh, from the front term, if you had kept it factored,
Mm-hmm.
with if you had sine of 2x times 2, then
Mm-hmm.
you have 2 sine squared x, which is what you had at the bottom of the other one. I think if you.
But there would also be a cosine factor in here.
What are the cosine factors come from?
Well,
Oh, no.
you're saying if you leave it like this?
Yeah.
If you leave it like that, then you
Uh-huh.
can factor out all the sine of 2x's
Mm-hmm. From here?
from there, yeah, from the whole
Yeah,
thing.
that cancels with the
Because
first
then you would
one.
get a 2 sine x
No, no, no,
squared.
it wasn't that bad.
No, you're close, you're close.
Yeah, so sine 2x,
Yeah, and then the 1 minus 2 sine.
1 minus cosine
And
2x.
then do the double angle on the cosine of 2x.
Uh-huh,
You
and
get that
this is,
sine of
and
x
there's a
squared.
sine x here,
2
2 sine 2x, sine squared x, and then you're saying factor out the sine 2x.
From the whole thing, yeah. And then do the double angle, cosine of 2x, and I think it
So
works.
sine 2x, so I'm just gonna use big brackets, 2 sine squared. I factored that out, so I got still minus, and then in parentheses, 1 minus cosine 2x. All right?
Yeah.
But you need to go back
And
to
now do the
the,
double-
And then the double angle for this?
yeah, and then the 1s will cancel and the 2 sine, well, actually,
The 1 won't cancel, but the 2 sine of x will
well,
cancel.
because there's gonna be another 1 in there, and it's gonna.
Minus
flip the
1
positive
plus,
and
and
negative.
cosine 2x could be written as, what was it? 1 minus,
1 minus 2 cosine squared x.
or is it 1 minus 2 sine squared, I hope?
It's either 2 cosine squared x minus 1.
This is what I need verified. Does that equal 1 minus 2 sine squared?
What was the other one, Justin?
So this equals each other. 2 cosine squared x minus 1 is equal to 1 minus 2 sine squared x. I don't think that's it.
1 minus 2 sine squared x.
Cosine 2x has 3 identities.
How did we find
I'm
that?
going
On the internet.
Help us, Gargle.
From one of them, you can get the other 2.
Okay.
It's just the double angle.
I'm doing.
It is sine squared minus cosine squared. That's one I'm pretty sure about.
Yeah, sine squared minus cosine squared, 2
And
cosine
then,
squared minus 1.
and then if I replace cosine squared with 1 minus sine squared. And I get
Squared x
2
minus 1.
sine squared minus 1?
Yep.
How do you get cosine
Oh,
2x
that's
equal to?
Wait. Sine squared.
No, he's right. That is the identity right there. Yeah.
Cosine squared is equal to 1 minus 2 minus
Yeah.
sine squared. That works.
That
I'm
works.
just not sure about the sine squared minus cosine squared because I haven't taken.
Or is it cosine squared minus sine squared, I think? I hope.
It's cosine squared x minus sine squared x.
Okay, good. Cosine minus sine squared.
Yes.
Right?
Yes.
Okay, now replace cosine squared with 1, okay, the Pythagorean identity, 1 minus sine squared, minus another sine squared,
Now you get 1 minus.
gives us 1 minus 2 sine squared.
Yep.
So now it's sine x times 0.
Mm-hmm. And which is identically 0. That's the one thing about the Wronskian It's kind of hard to make that clear, but it has to be identically 0 over that interval that we're talking about. And this is identically 0. No matter what x is over any interval, this is identically 0. They use that. And so linear independence is that if you can show that there's at least one spot in the interval where the Wronskian is not 0. It doesn't have to be non-zero over the whole interval. It just has to exist at least one spot where it is non-zero. Usually you get that it's never 0. Good. Okay.
That was a fun one.
That was awesome. Okay. All right. One thing I got for you now, instead of sort of recap, it's been a week since we had new material, right? No, last week we had an exam. We didn't have class this last class. So last session we didn't have class. So it's been a while since we've had new material. So this sheet is just a sort of big picture recap of ideas from 3.1. Okay. Instead of just writing this down in our notes. All right, so 3.1 is specifically talks about second order linear. 3.3 moves on and talks about general linear, general nth order, so any order. Okay? And they try and develop the ideas in 3.1 specifically for second order linear. And then in 3.2 and 3.3, those ideas are generalized for nth order. All right. So general form like this, you could have these coefficient functions. You could have one in front of the y double prime. They talk about if you divide every term by a of x, as long as it's not identically 0, which it wouldn't be because then it wouldn't be a second order differential equation. You divide through by that, and they write that in standard form for the second order linear differential equation. Now, if there is some function over here, it's called non-homogeneous, right? If there is some non-zero function on the right, non-homogeneous second order linear. Now, with that equation, with that differential equation, it's associated, so it's partner equation. The associated homogeneous equation occurs when we consider the right side to be 0. And there's going to be a relationship, okay? Here's the regular equation, non-homogeneous. It's associated homogeneous. We drop that function and do 0. So we talk about methods of solving this, and then we talk about how that helps us solve the general one. There's a little blurb at the end of 3.2. Okay. Anyway, so some bullet points, the homogeneous equation. We saw some things. If y1 and y2 are any two solutions of that equation, 1, then any linear combination is also a solution. Okay. That doesn't talk about linear independence or anything. It just says if I have two solutions of that equation, then any linear combination is also a solution. Now, the stronger statement, if you can find somehow, if you can identify two linearly independent solutions, okay, then not only is any linear combination of those two functions a solution, but the converse is true. Any solution out there in the world to that equation is of the form some linear combination of those two solutions. So that is the general solution. Okay? Every solution will be some linear combination of those two. That's a big result, and that holds in higher order as well. And then to determine linear independence, we do the Wronskian like we did before. Okay, Wronskian to determine independence or dependence of those functions. Okay. This is going to be a big case. If the coefficients of this linear equation are constants, we try y equals e to the rx as a solution. Okay. And we're going to do a little bit more with that today and look at all the different cases. So it results in the characteristic equation. We talked about that when I sub y and its derivatives into equation 1. We get a characteristic equation involving r. The solutions to that become the separate functions that the separate solution functions. One for each value of r you get. All right. So we did see a couple of cases here. In the case of a second order, the characteristic equation would be degree 2. It would involve r squared only. You can have at most two solutions. In fact, if you consider complex numbers will have exactly two solutions. So the possibilities are you have two distinct real solutions. Distinct meaning different from each other. That's the simplest case. We could have a repeated real solution. For instance, r equals 1, but it has multiplicity 2. So if the characteristic equation was r squared, r minus 1 squared equals 0, then 1 is the only solution to that. Right, no, sorry. R squared equals 1. No, there would be 1 negative 1, 1. Anyway, we could have a repeated real solution. In other words, a multiplicity 2 solution to that characteristic equation. There can also be complex solutions. We're going to look at that today. Okay. You could have purely imaginary or true complex solutions. Okay, but this is the big method. In fact, 3.2, 3.3 restricts itself to just constant coefficients. Okay, linear constant coefficients. So this is our main method of attack. Okay, another thing about existence and uniqueness. So P of x and Q of x, if those are, those are the coefficient functions. If those are continuous, so over some open interval containing the point A, so if A is interior to that interval, then equation 1 will have one and only one solution. So there exists a solution and only one solution, and this is a particular solution that satisfies these two conditions. So notice, a first order linear equation, we only needed one initial condition. Second order, I need a condition involving the value of y and the value of y prime at that specific point A. So I need two initial conditions to lock down a particular solution. Okay. This can also be translated to higher order, third, fourth order differential equations. I would just need more initial conditions to lock down a particular solution. Okay. So what we're going to look at is that these concepts do translate to higher order linear differential equations, so nth order. Okay? So let's start off there. We're going to do a couple more examples, one more, of second order, and then we're going to move on to higher order. Okay. So with 3.1, we're going to move fluidly and talk about 3.2 and 3.3. They all deal with the same concept. Okay? So let's look at an example. Consider the equation. This is second order, y double prime plus y equals 0. So it's homogeneous and constant coefficients. They're both 1. So now it wouldn't take much. In fact, we did this problem like the first day just to verify, but we did verify that cosine x solves that, as well as sine x. Okay, so they're both solutions. You can find that because find the second derivative and plug the second derivative and the original function, and you get an identity. Okay. Oh God, where'd it go? Need something to focus on. All right, so, and these are linearly independent. If you did the Wronskian, it would show that neither is a multiple of the other, a constant multiple of the other. Their graphs oscillate, so it's not just a vertical, it's not just a multiple of the other. So, since they're both linearly independent, we could say the general solution takes on the form C1 times cosine x plus C2 times sine x. This is the general solution. Right? All right, now, what is our method of attack, though? If it's constant coefficients, and I said, hey, if we assume, taken on, that the solution is of the form y equals e to the rx, right? What would the equation become? Y double prime, and what's the second derivative of that? R squared e to the rx. So if I put all of that in there, plus y, and y is just e to the rx, equals 0. And the e to the rx never goes away. And of course it never equals 0. So this is totally equivalent to the equation r squared plus 1 equals 0. And what are the solutions to that? What's that?
R equals 0, -1.
0? When? Ooh. -1? Does -1 work? No. Oh, no. This is the same as r squared equals -1, isn't it? Yeah. So what are the solutions to that? I. Oh yeah, that's the imaginary unit I. But also negative I, because if you square negative I, the negatives drop out. I squared equals -1 as well. So plus or minus.
Can you write J?
No. That would not be right.
Why J? What's this?
Because electrical engineers use I for current.
Right. And mathematicians also use I as a basis vector. Yeah. But I is the imaginary unit, square root -1. Okay. So one thing to recall way back at this point from 112. So we would take our functions to be of the form, y equals, well, it was e to the rx, so it would be e to the ix. That was my first solution, r equals I. Or e to the negative ix, right? And any linear combination. All right, so at this point you're dealing with, imaginary powers of E. One thing to recall, and this is Euler. Anything that's really super crazy, you usually do the Euler. And this is Euler's formula. It's usually posed as e to the I theta, but we could use x as well. E to the ix cosine x plus I sine x. All right. Therefore, e to the negative ix, and we could just keep the I part out and think of it as I times negative x, would be cosine negative x. But cosine negative x, cosine is an even function. Cosine negative x is the same as cosine of x. So that negative just gets absorbed. But sine of negative x is the opposite of sine x. Sine is an odd function, so that minus comes out front, and I get minus I sine positive x. So Euler's formula, and we can write these as in the form cosine theta plus I sine theta.
So can R have values besides plus or minus I? Because I did it with R being -1.
Mm-hmm.
And the second derivative of, e to the negative x is e to the negative x. And the first derivative is negative e to the negative
But there's no
x.
first derivative in that. It's y double prime plus y.
Oh,
So they would not cancel out.
okay.
Yeah, if it was plus y prime, you'd have a different characteristic equation.
That's why I was like,
You got r squared plus r equals 0. R
R
squared plus r equals 0, yeah, that's
Yeah.
where you get the solution 0 to 1.
Yeah.
0 to -1. Okay, so, oops, I want to write these, sorry, as D1 and D2. So not necessarily, we'll get to this. So D1, D2 represent some coefficients. All right, so a little bit of operating with this. D1 times and e to the ix, cosine theta, or cosine x, plus I sine x, plus D2, cosine x, minus I sine x. Okay. All right, now what I'm going to do is get the cosine terms together. It would be d1 cosine x plus d2 cosine x. So a couple steps of factoring and getting like terms together. It would be d1 plus d2 cosine x, and I'd have plus I times d1 sine x minus I d2 sine x. So I'm going to write this as plus I d1 minus d2 if I factor these. Factor out I and the sine x. So miraculously, even though we've got imaginary solutions to that characteristic equation, it's still a linear combination of cosine x and sine x, just like we know it should be because cosine and sine are both solutions to that equation.
Why doesn't the I go away? The I.
Oh, it's part of this coefficient. So I get c1 cosine x plus c2 sine x. Now this is the kind of interesting thing. d1 and d2 do not necessarily have to be real values, real coefficients. They could be complex coefficients. But through this process, d1 minus d2 times I will be a real number. Okay, and if you want to go through the details, we can do some examples. Same thing with d1 plus d2, and it turned out to be a real coefficient. So the imaginary parts would cancel out. Yeah, I didn't believe that either. I had to work out a few
I'm just
examples.
curious as to what the general logic. It seems like you would just have an I, like you would just have a factor of I.
But if d1 and d2 are complex constants, then times I, that can turn into a real number. Yeah. So they'll involve i's and
well.
yeah. So the idea is that yep, we get a linear combination of sine and cosine. Oops. Sine and cosine. Okay. All right. So that yeah, look at the book, and they don't do a good job of notating this. That these, even when we get complex solutions to the characteristic equation, we get real coefficients. So we got a real valued function. Yeah.
Why does it seem that eyes come back when it's convenient? But through my calculus courses, when you have something where you can't take the square root of a negative number, then you've done something wrong with your algebra. Or now it's okay for eyes to come back up. Is there a reason? Or?
Part of it is time. We could do an example.
That's up to the class, and you gotta know if we got it. Sure.
You're doing an
I don't
example?
mind it.
Okay.
Yeah.
Okay, so we got y double prime plus y equals 0. That's the original one, right? Okay. Say we have initial conditions. That existence and uniqueness theorem says that, and by the way, these are constant coefficients. My p of x, q of x. In fact, there is no y prime, but that's continuous. Those are continuous coefficient functions, p of x and q of x, because they're constants. So this says that there should be one and only one solution that satisfies a given condition, two given conditions. Say y of 0 equals 1, and y prime of 0 equals 1. That theorem, the existence and uniqueness, says that there should be one solution to that, and only one. And we saw that a general solution involves sine and cosine. Should be able to be written as a linear combination of those functions. Okay, well, that's not good. All right. So the function that we've got, call it d1 e to the ix plus d2 e to the negative ix. Okay, so if we leave it at this point, or do we want to write it further and say it was what, d1 plus d2 cosine x, right? Plus And what was this one? I times
D1
D1 minus D2 sine x.